Hi folks, this is a video/tutorial of the R2lab wireless experimental testbed over here at Hagia Sophia Antipolis. The major pro of this testbed really is about reproducibility, as our nodes are totally isolated from the outside world, and so you can be sure that you will not be affected by any other radio traffic than the one that you send yourself. So the major entry point is R2lab.inria.fr. But before we can see how it works, we're going to have to see how to do registration so that you can get an account. So here is the outline of what I will cover in the video. And in particular, we'll use a small experiment as a use case. It's a real one. And we'll discuss that before we actually get to running anything in this part. So in order to get an account, we go to the R2lab portal here. So R2lab is a federation of testbeds, mostly European testbeds, as it builds on the results of the FIRE program. So we have here Planet Lab Europe. We also have, for example, Nitos Volos in Greece, several testbeds in France, like for example IoT Lab, and here you can see R2lab as well. So you need to sign up, of course, if you don't have an account. And at this point, you need to select your institution in this list here. As you can see, there are quite a lot of them already. So if you're a member of European Academia, your institution is probably in there already. So let me show you how you would click. I would select, for example, this one. So it is part of the great advantages of this federation. The paperwork has already been taken care of. Right. So, signing up will require approval from the person in charge on your institution side. We'll call him your PI. And there's a workflow for that involving the usual flying of mails back and forth for checking purposes. So, we'll skip that today. What is important is you need an account as a user, and then you will need a slice that your account is a member of. So, let's see what this actually looks like when you log into the system. You can see here the slices that I'm a member of. Currently there's only one. So the name of this slice is onelab.inria.r2lab.admin. This is also the name of the Unix account that I will have to use on the gateway, so let's remember that. So when I click on this slice, I will be able to browse all the resources exposed by all the testbeds in the Federation. It takes some time to browse them all, but this is a handy feature for people who are interested in cross-based experiments. So for example, if I wanted to set up an end-to-end experiment to assess the performance of a deployed application with its servers and wireless terminals, then a Planet Lab node together with an R2lab node could come in handy. But for now, I will focus on R2lab. So as you can see, R2lab exposes let me first select the testbeds that I'm interested in. So if I filter out all the other testbeds, you will see that R2lab exposes a single node, or a meta node if you wish, and this is to materialize the fact that the testbed can only be reserved as a whole. Given that our major focus is on reproducible experiments, it would not make sense to share the testbeds, as two concurrent experiments could be in a position to interfere with one another. Good. So one thing to know is you need to have your slice attached to this meta node. So in my case, it's already done. But if it wasn't the case, I would click on this particular box and then apply the results so that I would do the change. All right. One other thing that you can do with the R2lab portal is to manage your reservation. And this is the purpose of this scheduler tab here. But in my case, I will show you how to do this on the R2lab itself. But before that, let's see what the experiment is about. Our sample experiment is about measuring angle of arrivals of the radio signal. So we want to assess and compare various techniques published in the literature, and we're also going to use this kind of results to calibrate R2lab itself so that we know the testbed better, so that we can actually measure if we have any kind of reflections, so that people can be aware of it and take this into account. The basics are pretty straightforward. So the requirements is you need to have two antennas aligned in a certain direction that you know perfectly well on the receiver side. And you also need these two antennas to be close enough that their distance is no order of magnitude of half of a wavelength, or preferably smaller. And given this particular setup, if you're able to measure the phase of arrival of the signals at the two antennas, using a very simple math, you can figure out the angle of arrival, which is essentially symmetric. So this method is not going to be able to say whether the signal comes through the right-hand side or the left-hand side, but they should be able to tell you the actual angle of arrival. So what do we need to do this? So you need a receiver node with the multiple antennas as we just described. You can then take essentially as many sender nodes as you wish, except that you need to be able to capture CSI information, and for this there is a requirement to use Intel cards. In our case at least, we need a specific tool set published by Intel. So, and in theory that's all that you need, but it's actually not that simple. And we found out that we were able to get very stable and reproducible results across multiple runs, except that if we ever reset the receiver node, then we were starting to see another set of still stable and reproducible results, but different from what we had before the reset. And in order to work around that, we came up with this idea of using what we call a Polaris node. A Polaris node is supposed to be situated right in front of the direction of the antennas, meaning that the signal coming from the Polaris would have the same phase when reaching the two antennas on the receiver side. And so we're using this particular first measurement in order to translate everything that we measure for the other nodes, and this turns out to give us reasonably accurate results. So we decided to use node number 5 in our testbed, and the only requirement that we have again is to use an Intel card, and this is the reason why we haven't been able to use these nodes 1 to 4 1, 2, 3, 4 as sender nodes, but we've been able to come up with a rather representative set of directions. And with these nodes selected, we are now going to be able to move to the actual data collection part of the presentation. Okay, now I want to run this experiment. So I will show you how to prepare the testbed and run the experiment that we have implemented as a NEPI script. I have prepared a screen with a browser, a terminal on my laptop, and then a few notes that I will use for cut and paste into the terminal. So first of all, let's go into the R2lab portal, and just before I log in, I can already see a few information on the testbed, like what kind of things you can find in the testbed, the details on the nodes in terms of hardware, radio spectrum and these kind of things, plus a few tutorials on well, essentially what we are going to cover in this video: registration using the gateway and the basics on NEPI. Now, in order to run the experiment, I'm going to log into the system, and for this I'm going to use the exact same credentials as the one that I gave when I registered with R2lab. Once I do this, I find two new tabs here, one giving me an idea of the reservations that have been done, and another one giving me, let's say, an overview on the status and the leases, what we call leases, the reservations that have been done. So in order to prepare the testbed, I'm going to log into the gateway, what we call the gateway, which is named faraday.inria.fr. So I'm going to use the same slice name as the one I had with R2lab. The name here is R2lab INRIA R2lab admin, and from this point I can use very basic tools to essentially turn nodes on and off, and also to load images, and this is what I want to show right now. So the first thing I'm going to do is looking at the set of images that are available to me. You can see at the beginning, let's say, very common and basic images based on Ubuntu, Fedora. We also have some GNU radio oriented images for US RP nodes, and we also have open interface that is in the work right now. So I'm going to use this particular image, which is called Intel CSI. It comes with some tools shipped by Intel that have everything we need to capture channel state information things. And in order to load them on my nodes, first of all, I need to define the set of nodes that I'm going to work on, and then I can load my image on these different nodes. So the interesting thing here is that uploading images is done using multicast, so essentially in parallel. So loading an image essentially takes something in the 2 minutes. Most of the time, part of the time is spent waiting for the motherboard, so we cannot do much better than that. So while this is going, you can see the map here is actually essentially not exactly real time, but it's reasonably up to date, and you can see the state of the different nodes. So to keep it simple, the bigger the circle and the closer to being ready. And so when it's green like this, it's essentially uploading, and this is what we see. All right, so let's wait for a little longer. Yes, one thing we can note is that this particular mode is graphical, so that we can see the details of every upload. And for this reason, at the end of the upload, I'm going to be prompted for a key so that I can have a view on what has been doing. But of course, there's a version of this same tool that can be used in a script. So essentially, I could have tweaked my experiment script so that this particular preparation phase could be handled. I just decided that it was really more helpful for people, and especially for newcomers, to have a first sense of how this works for the beginning. Okay, now that the nodes are ready, I can get out of the gateway. This is all we're going to have to do on the gateway, and go back to my laptop where I will be driving the rest of the experiment. So again, I'm going to have to define the scope of my experiment, because it's another shell, obviously. And I'm going to send the experiment itself. So while it runs, I'm going to explain what it is that we're doing. So we precise the name of a directory where we want to store results. We give the name of the receiver, the senders. We give some parameters on how many packets we want to send and this kind of things. And now I'm going to type Ctrl-Q so you can see the rest of the beginning. So let's see what it gives on the first node. We have, well, some details on what is going on. The essential thing is that the experiment is designed like this. For each couple of nodes, we want to do initialization of the receiver and the sender essentially at the same time, and then make sure to synchronize at this point so that the sender and the receiver are, of course, working together. And at the end, we want to do the data collection. While the script is running, let's take a look at what the code looks like. So our code is made of two files. One is Python, which uses NEPI and is about running this orchestration diagram for each couple of nodes. And the other one here is written in Bash, and it contains the details of every little phase here, so that we use the two languages for essentially for what they're good at. Before I go any further, you can also take a look at the code right here in GitHub. So there are essentially these two files here that you can review by yourself and use if you want. So the Python code essentially has one big function that does one run, essentially one node, one receiver node, one sender node. And for doing this, we're using, as I said, NEPI to create this central object, which is going to be the main driver for the whole experiment. And in this object, we add two nodes, one for the receiver, one for the sender, of course. As you can see here, we have the ability to address these nodes through the gateway, because we, of course, do not have a direct SSH connection from my laptop to the node, so we need to go through the gateway using SSH. So this is what these lines are for. And then in each of the nodes, we will instantiate what we called application, which is essentially a process, right? And in order to be able to easily cooperate with the shell script, we use the same shell script as the source for each of the application. It's just that we're using a trick that we using this shell script with a subcommand that's going to specify which of the 4 phases we are talking about. So this is how the 4 phases are described. Each of the phases are connected to the node where the application is expected to run. And then in order to model synchronization, we have instances like this, which lets us just have the 2 phases run in parallel, and we're going to exit this particular wait finished function once the 2 phases are done. Very basic stuff. Of course, we could have used more sophisticated mechanisms, so we could have added dependencies between the phases, and we could just wait for the last one of the phases, and NEPI would take care of everything. So that's essentially it, and at the end we're using some built-in NEPI capabilities to gather the output of the different processes. That's essentially it. Then the main is just a wrapper that implements arguments so that what are the receivers, what are the senders, where do I want to keep the storage. And well, a little convenience here to just be able to name nodes by number instead of by name, but that's really straightforward. And then we just do a loop on each couple of senders and receivers, and that's it. As far as the bash script is concerned, we have a few convenience functions that let us show some details on the system so that we can do forensics afterwards, making sure that everything was running as we expected. And then a few utilities to find out about the name of the different drivers, wait for them to come up, and this kind of things. It's pretty basic. It could go in some sort of a library, but it's not really convenient for bash scripts. So for the tutorial, it's better to have them right inlined. And then for each of the 4 phases, we just have one bash functions that do whatever you need to do on the nodes. Typically here, I want to unload the drivers, reload it with a specific flag, then configure a monitor interface. Well, this kind of things. It is really pretty basic. Then for the sender and receiver side, we just use CSI tools essentially as is, and this is where we, for example, use the parameters that were given on the command line. The little trick is about the receiver that essentially does some computation to estimate how long it should be listening. So this is the place where we add some let's say extra safety. To be extremely safe, we also record the checksum of the output. And then at the end, we only have a simple wrapper that can dispatch the code depending on which phase we are on. This way, we can have a very simple organization of the code, and we can easily share code between the different phases. It's pretty straightforward. All right, so just before it finishes, let me show you what is the output of all this. Essentially have now a directory here, which is the name I provided when I started the experiment, and then this is where the results are going to be stored, and here is the real file that we're interested in. This is the naming scheme that we have implemented in the Python script. We have an output name that we will be able to feed into the post-processing tool, which are written in MATLAB, and that we're going to see right away. Okay, so let's quickly see how this data is post-processed with MATLAB. As an input, of course, we find the raw data as collected with NEPI. We can then apply the various methods we wanted to assess, which allows us to build a summary plot with the nodes on the x-axis at the place that shows their actual angle. So for example, around -70 degrees, we would find node number 7 that has the closest angle to the antennas line. On the left-hand side, we only show the most prominent value found by each method, knowing that music and MVDR actually come up with a continuous curve, with possibly several peaks that you can see on the figure on the right-hand side, and that we can also inspect individually for each node using this small MATLAB GUI. This concludes the presentation. Thank you for listening this far. You now know enough to start writing your own experiment using R2lab and NEPI. If you run into any trouble, do not hesitate to get in touch with us on one of those mailing lists. Okay, cheers!